pale ring appears on the weather maps first, a clean circle of pressure cresting the oceans as if the planet were a drum and someone had struck it once with an invisible mallet. Ground stations blink and record a nudge. Not violent, not loud, yet coherent across half a world. Hours later, the ring races on, crossing mountain chains, deserts, and cities that never notice. It is a thing you can see only by instrument, an outline of motion that refuses to fade. Then another map, not of the sky but of the night, shows the continents as veins of light. For a moment, the veins flicker. Somewhere a hospital tests its backup power. Somewhere a data center hears every fan rise in pitch. The sky looks calm. The instruments do not agree. We live inside a web. The web sits inside fields, and the fields pour from the sun. Most days, the sun is more gentle than the weather, a patient source of heat and photons. On a few days, it sends ropes of plasma and magnetic knots that recoil into space. When those knots arrive, the Earth answers with its own songs, fluttering curtains near the poles and currents that crawl through the wires beneath our feet. A city is not a fortress. It is a musical instrument, wired to a star. The paradox is simple to say and hard to feel. The most dangerous storm might be the one that leaves the sky looking normal. Look again at the ring. It does not break windows or topple cranes. It leaves a signature that goes around the world and comes back, a wave that refuses to die while the atmosphere keeps the beat. If a pressure wave can circle the globe, what else can? If a signal can propagate that far without tearing anything apart, what does that imply about how delicately our world is tuned? Our sensors hear before we do. Our networks strain before our eyes suspect. We are built on moving air and moving charge, and both are ruled by patterns we did not design. Imagine standing on a shoreline before dawn. The air is cool. The sea is flat. A faint hiss rises from the surf. Nothing in your senses hints at the loop of force arcing overhead, or the thin river of electrons that may choose tonight to change course. You step back inside. A bedside clock hums. A phone on a table draws a tiny sip of current. If the sun sends an instruction strong enough, both will keep perfect silence. Why should an event so far away decide whether the fan turns or the heart monitor stays awake? How much distance turns beauty into harm? How much warning do we really have when the warning is not light but pattern? The first clue is always the instrument. Metal cups turning in the wind, quivering needles, GPS baselines that stretch and contract by millimeters, magnetometers that write their diaries in lines as thin as hair. That ring on the weather map is both a curiosity and a measurement of connection. Nothing is isolated. The atmosphere talks to itself across oceans. The magnetosphere talks to the crust by coupling through fields. Our machines sit at the crossing of these languages. They hear everything, and sometimes they answer by failing. A line trips. A cascade begins. A city goes dark, as if a giant were pinching the artery. People step outside and look up because that is what we do when the lights die. But the sky offers no clue beyond the quiet of stars. In everyday language, the world is more wired than it looks and more fragile than we admit. A hospital knows this and rehearses. A bakery finds out when the ovens stay cold and the dough rises into defeat. These are not apocalyptic images, only human ones. They matter because a civilization is a sum of such minutes. We overbuild for wind and water. We accept that rivers flood. We forget that space has weather too, and that on rare days the storm comes not as rain, but as an equation that every wire must solve. Here is the paradox, sharpened by scale. A shock wave in air travels vast distances, passing like a rumor from pressure cell to pressure cell, completing a loop while we go about our routines. A solar disturbance travels far greater distances and arrives not as shock in air, but as a change in the invisible scaffolding that guides charged particles. The first does little to us, yet it maps the reach of our atmosphere and the harmony hidden there. The second can do much to us, yet it often looks like nothing at all. Do we fear what we can see or what we can measure? Which is the better teacher? The drifting aurora that paints the night, or the substation that does not wake after midnight? You could ask whether our age is simply louder with data, whether we are inventing threats because we have more maps. The answer is neither comfortable nor theatrical. We have built a stacked tower of dependencies. Electricity is not a technology. It is the preface to every other technology. Purifying silicon to make logic takes temperatures higher than most natural fires. Forging the steel that holds bridges requires heat and fuel that tie back to grids and mines. A supply chain is a biography that begins with rocks and ends with intentions. And every chapter has a power requirement. If a storm chooses the right hour, it writes marginalia in the biographies of millions. We test our world by accident and by design. Satellite constellations become a lattice of eyes. They see wildfires build their own storms, towers of smoke that punch into the upper air and seed lightning inside their ash. They see volcanic plumes drift beyond the reach of a single country and dim the world a fraction. Ground systems feel the tug of the sun long before it paints the aurora. In quiet years, these measurements read like poetry. In hot years, they read like instruction. Measure the ring. Follow the current. Compare the strain. Explain the part that failed. The verbs are plain. The meaning is not. Questions pile up because they must. What fails first when light arrives as instruction rather than heat? How long can a city breathe without wires? If the map of risk looks beautiful from orbit, does that beauty dull our urgency? When the sun knocks, who decides whether we open the door? If warning lives mostly in the memory of instruments, how do we teach humans to listen? The ring in air is a messenger. It tells us that the planet is strongly coupled to itself. The geomagnetic flutter is another messenger. It tells us the planet is coupled to space. Machines let us overhear both conversations. A barometer in a village reads a trace that matches one recorded in a desert a world away. A coil buried near a dam records a whisper that matches one under a tundra road. Our global nervous system is unintentional yet sensitive. We did not build the atmosphere. We did not build the magnetosphere. We built microphones inside them, then used those microphones to wire our sinews to markets and medicine and dreams. There is another image to hold. Night on Earth from orbit. The glowing filaments of cities and highways. Watch a filament dim, then brighten, then dim for longer. Zoom into one thread. A mother warms a bottle using a kettle plugged into a wall. A nurse squeezes the hand of a patient and watches the line of a monitor. A farmer opens a cabinet and sees seeds held at a promise kept by cold. We say resilience. But mostly we mean people. And yet resilience is also physics. A transformer does not care. A cascade is obedient to threshold. A relay will open when it must. Being human helps the morning after, not the second a surge arrives. If all this sounds remote, bring it closer. Suppose a pressure wave circles the world again next week. You will not hear it, but 100,000 devices will mark its passing. Suppose a bright rope erupts on the sun a month later and our planet meets its thrown field head-on. You might not notice it in the clouds. You might notice it as a pause in a subway, a jail of elevators, a cashier saying cash only. If the scale is larger, you will notice it in the silence that follows a click when nothing starts again. The sky will still have that serene look that fools painters. The storm will be data, and data is hard to stare at. We begin, then, with an agreement to see like instruments for a while. The camera will stay wide enough to hold oceans, then pinch down to a dial that twitches in a shed on a hill. The microphone will sit where fields are strongest, then move to a kitchen where the fridge turns itself back on with a complaint you can hear across the room. We will keep images close to things you know. The shore at dawn, the hum of a clock, the way a city feels when every sign goes dark and you can hear your own shoes again. We will test 8 doors to collapse, not to indulge fear, but to learn which hinges creak and which frames hold. We will also do what a rehearsal demands. We will pause where failure begins and ask whether design could have moved the threshold. We will tally what depends on what, without scolding and without romance. Some teams argue that the ring in air is trivia. Others say it is a teacher. The debate is less important than the method. Follow the trace. Compare across continents. Test the same event with another type of instrument. If the story holds across methods, it belongs to the world and not to the storytellers. That is the tone we will keep. There is a human reason to care, which is the only kind that endures, not the skyline, the shifts inside rooms, the routine that wraps a life, heat at a tap, cold at a switch, a call that must go through, a door that must open because a code says it should. When those become rare, people move, or people fight, or people start again. A civilization is a way to avoid that choice for as many as possible, for as long as possible. The map we are building helps with that aim because it points to small moves that buy large hours. A spare transformer in the right county is not a metaphor. A backup for a chemical plant is not a luxury. A line trimmed from trees is not a poem. These are the dull, brave acts that move thresholds by inches. Think of the planet as a set of coupled oscillators. Air talks to water. Water talks to rock. Rock talks to metal and wire. Wire talks to finance and food. When a push arrives at the top, it does not fall like a hammer. It rings like a bell and the tones interact. Some cancel, some amplify. The pressure ring is a visible tone. The geomagnetic surge is an invisible tone. Our task is to hear the chords before they grow into a note that breaks glass. This is not mysticism. It is practice. You can learn to feel the room you are in by its sounds and its drafts, and still be a person whose feet are on the floor. So we sharpen the big question. What truly threatens a civilization first, the ground beneath, the sky above, or the fragile web we spun between them? There are numbers for each. There are models. There are honest disagreements and clean experiments. There are gaps you can drive a truck through. That is why the argument is worth the hour. If the first failure is a tight coupling in the grid, then we buy time there. If the first failure is ash that steals a bit of light for a year, then we buy time in fields and stores and lungs. If the first failure is the habit of ignoring small warnings because they are not photogenic, then we buy time with drills and stories and maps. The ring on the maps is an invitation as much as a warning. It says the world can carry a message around itself in a matter of hours. We can do the same if we mean to. Build sirens that speak in voltage, not only in sound. Train eyes to see a pattern, not only a cloud. Teach that a night sky can be dangerous and trustworthy at once. None of this asks for faith. It asks for attention. Attention is the cheapest defense that still works, and the hardest to keep. We are ready to begin the examination. The camera will dive from orbit to a sheet of water. The microphone will switch from coils under snow to a buoy that feels the pressure of the world pass through it like a long, slow drumbeat. The first door is not a city and not a star. It is a basin that behaves like a lung. The signal we chase comes from the sea. For more evidence-led analysis, like and subscribe to the Quiet Universe channel. Our first stop is the sea, where a pressure note writes its signature into the open water and points us toward the signal in the sea. The sea keeps its own clock. Waves follow the pull of the moon. Currents follow the memory of heat. And deep beneath them, another rhythm moves, slower and harder to name. When the first barometers caught a global pulse after a far-off explosion, scientists saw not one shock, but a sequence, wrapping around the world like ripples in a boundless bowl. Each loop took hours. The energy that remained was far smaller than the blast that started it, yet it refused to vanish. The atmosphere had behaved like a skin stretched tight over the water, carrying a signal that could not be heard, but could be measured. The sea answered in turn, rising and falling by millimeters, whispering back through pressure sensors fixed to cables and buoys. It was as if the ocean had listened to the sky and decided to respond. Ships at sea have always been ears for the planet. They record tremors that move through water long before land stations know what happened. A cargo ship crossing the Pacific once reported a strange stillness, not of calm, but of synchronization. Every swell seemed to fall in step, the surface tightening into uniform motion. A few hours later, the same pattern appeared on wave buoys near Hawaii and South America. The disturbance was too regular to be a storm. When the data were assembled, the truth emerged. The ocean had carried a ring of pressure created by a single event thousands of kilometers away. It was a drum hit the size of the world, audible only to instruments. Yet it left the planet vibrating in harmony. A paradox hides inside that observation. The more stable a system looks, the better it can transmit motion. The calmest ocean can pass a pulse with almost no loss. So too with our atmosphere, which is thin and elastic enough to behave like a single resonator. When a volcanic eruption pushes air upward, it is as if someone has struck the planet's bell. The sound travels through both air and water, echoing back and forth until friction turns it into heat. But before it fades, it teaches us about the structure of the world. By timing how long the pulse takes to go around, we can calculate the speed of sound at different altitudes, the density of air at different layers, and even subtle shifts caused by temperature gradients. A ring that begins as destruction becomes a diagnostic tool. In plain terms, nature itself performs the largest experiments imaginable, and we are still learning how to read the results. One ring might pass unnoticed by people, but reveals secrets about the balance of gases that protect us. Another could expose how tightly the seas and the sky are coupled. For every shock, there is an echo, and every echo carries data. We are only now learning how to translate it into meaning. When satellites mapped one of these global rings, they noticed something odd. The pulse reached a region of cold water and seemed to linger. The waves shortened. The amplitude increased, as if the sea had momentarily stiffened. Later analysis showed that the local weather had produced a temperature inversion, trapping the sound in a shallow layer where it could circle like a ghost. The pattern was identical to the way certain musical instruments store energy between layers of material. Earth itself had created a resonance chamber where air and water spoke to each other for days. The phrase, "the signal in the sea," became shorthand among researchers for this kind of haunting repetition, a reminder that even chaos has harmonics. And if you stood on a cliff above that water, you would see nothing but sunlight trembling on the surface. Yet the instruments below would be writing history in numbers, small rises in pressure, tiny variations in salinity, subtle vibrations on fiber lines. What matters is not the violence of the event, but the clarity of its path. Each measurement is a fingerprint of the world in motion, a mirror showing us what connects continents beyond sight. Why does this matter? Because understanding how signals travel through the Earth tells us how energy, and by extension danger, might spread through systems built upon it. The same physics that lets a wave race through air and water also governs the networks that tie our civilization together. Under the sea, cables carry most of the world's information. Each strand of glass fiber transmits the pulse of human conversation, and each cable is vulnerable to the same movements that shape the planet. When the seabed shifts, when a pressure wave passes, when a current changes, those signals meet. Engineers build slack into the lines, coils on the seabed to absorb tension, yet some events stretch the design. A pressure wave traveling fast enough can cause minute compression in the cable itself, distorting data flow. The irony is striking. A shock that begins as a geological or atmospheric event can ripple through the same medium that carries news of its existence. We once assumed that oceans were barriers, the dark silence between islands of civilization. Now we know they are mirrors, reflecting every push and pull. Sensors placed along continental shelves detect anomalies that seem unrelated until compared across the globe. A storm in the Indian Ocean can be traced through Pacific instruments hours later. The sea functions like a vast telephone, transmitting not sound but compression patterns. These patterns, invisible to the eye, reveal how tightly coupled the Earth's systems have become. the sea is not separate from the sky. The pulse of one drives the rhythm of the other. Think of it like this. The planet has chords. When one is struck, others resonate. The ring that travels through air can nudge the ocean. The ocean can nudge the crust. The crust can release energy back into the air as vibration. Each domain talks to the next through pressure and motion, not language, but resonance. To understand how energy moves through these layers is to hold a partial key to prediction. The challenge is not measurement, but interpretation. We collect data faster than we can think. Machines hear more than we can explain. Somewhere in that surplus of signal lies the difference between foresight and surprise. A group of researchers once placed a network of hydrophones across the Pacific floor. They were meant to monitor whale migrations. But they picked up something else, a low, uniform hum that persisted for days. It came and went in bands of frequency too regular for biology. After much comparison with satellite pressure maps, they realized it matched the aftermath of a volcanic eruption thousands of miles away. The ocean had become a wave guide, focusing the sound until it arrived as a nearly perfect tone. Nature had turned disaster into music. That discovery changed how scientists approached underwater acoustics, and even how they studied climate, because it proved that the sea could carry coherent information over planetary scales. Why does that hum matter? Because it shows that no event on Earth is entirely local. A pulse strong enough can travel through the interconnected mediums of air, water, and rock, carrying both its violence and its lessons. The same principle applies to human systems. A power surge in one country can ripple through grids in another. A supply shock in a single harbor can reshape economies an ocean away. The sea, with its indifferent transmission, is the oldest model of globalization we have. Understanding it is understanding ourselves. At its heart, this chapter is about attention. The signal in the sea is easy to miss because it hides in plain symmetry. No lighthouse will flash to mark it, no storm cloud will announce it. But the instruments remember. A pressure gauge in one hemisphere will register a whisper identical to one on the opposite side of the world. That unity tells us that Earth's thin shell of life floats on a drumhead always in motion. What we mistake for stillness is only the long tail of a ringing world. It is worth pausing on the human scale again. Fishermen have reported strange changes after distant events, waters rising and falling with no wind to drive them, a calm that felt wrong. These experiences once lived as folklore. Now they read as data points. Our ancestors were the first sensors, tuned not by equations but by instinct. Today, satellites extend their reach, translating intuition into measurement. Yet we risk losing the emotional weight that made those instincts valuable. If a storm in the sun can alter the patterns of our seas, then the boundary between myth and measurement is thinner than we imagine. A final paradox emerges. The more we know, the more we realize how delicately balanced everything is. Instruments detect oscillations in the deep that coincide with oscillations in the ionosphere. These linkages suggest that the planet behaves as a single resonant body, its solid parts and its fluids moving in sympathy. It means that a single disturbance, properly timed, could affect multiple layers of our environment. That is both beautiful and unsettling. Beauty because it reveals unity. Unsettling because unity means vulnerability. A bell rings because it is whole. So the story of the signal in the sea becomes the story of communication itself. The Earth talks through motion. Every pulse is both an alarm and an opportunity. An experiment written in the language of waves. If we learn to read it, we might foresee the next great test before it reaches us. If we ignore it, the echo will arrive unannounced, and we will call it fate. The next time you look at a calm ocean, remember that it is anything but silent. Beneath the glitter of sunlight lies a conversation older than words, and the next chapter of that dialogue begins where the solid earth moves beneath a quiet coast. At first, the coast looked calm. Waves broke in their usual rhythm. Gulls hunted in the foam, and the air carried the same salt scent that had clung to that shore for centuries. Fishermen went about their work, pulling their nets in the pale morning light. Yet beneath the calm, the ground was shifting. The change was so slow that even the instruments hesitated to believe it. Satellites orbiting above began to notice a strange pattern, a rise measured not in meters but in centimeters, unfolding over months. What was once a level shoreline was lifting, and the sea was quietly receding. The discovery came through a technique called interferometric radar. From orbit, two radar passes taken days apart could be compared, revealing the smallest motion of the Earth's crust. When scientists overlapped the images, they saw colored bands, concentric lines like ripples frozen in stone. The coast had tilted upward, but no large earthquake had struck, and no tremor had been felt. It was as if the continent itself were breathing, exhaling once through rock and returning to stillness. The pattern repeated again the following year. What could lift a coastline without breaking it? In plain terms, imagine a giant hand under the crust, pressing up softly enough not to crack the surface but firmly enough to move it. The cause was not simple. In some regions, fluids deep underground can shift pressure, inflating cavities or lubricating hidden faults. In others, magma might be on the move, creeping through old channels that do not reach the surface. Both explanations fit part of the data, but neither explained everything. The uplift was too broad for magma, too slow for fluid pressure. It was a mystery written in topography. Villages along the coast began to notice clues of their own. Wells near the shore turned brackish as fresh water shifted underground. Mooring posts leaned at odd angles, though the sea itself had not changed level enough to explain it. In some harbors, the tides arrived minutes off their usual schedule. These were not disasters, merely whispers of imbalance. Yet taken together, they painted the outline of something vast. Beneath the quiet coast, forces were rearranging themselves in silence. Every so often, a tremor would pass through the region, shallow and brief. Seismographs traced small quakes clustering along a line that did not match any known fault. The pattern looked more like a zipper being slowly pulled open. Each slip released barely enough energy to rattle a cupboard door, but the sequence continued for years. This was not the usual aftershock pattern that fades over weeks. It was a swarm that seemed to breathe with the same rhythm as the uplift. The Earth was speaking in a language of increments. Why does that matter? Because the crust beneath our feet is not a single slab. It is a mosaic of stress and relief, of locked pieces that can store strain for decades. When one piece moves, the others must adjust. The uplift along that coast suggested a redistribution of mass on a regional scale, a rebalancing act that could influence nearby faults already close to breaking. A small shift here could mean a major release somewhere else. Earthquakes, like debts, can move before they are paid. The paradox deepened when GPS stations inland recorded the opposite motion. While the coast rose, the valley behind it sank by a few centimeters. It was as if the land had pivoted on an unseen hinge. The data implied an expansion below, perhaps a cavity forming or an injection of fluid. But there were no thermal signatures, no signs of magma rising. Instead, the crust itself seemed to be flexing, adjusting to some invisible load. A scientist looking at the map said it best. It is as if the planet is rearranging its furniture without telling us why. To put it another way, the Earth breathes through its faults. Pressure builds in one chamber and releases in another. An endless negotiation between gravity, heat, and the slow cooling of a world that still remembers its fiery birth. Most of the time, that conversation stays quiet. Occasionally, it clears its throat. The quiet coast was one such clearing, a murmur from below hinting at the unfinished nature of the planet. There was one clue hidden deep in the data. Long before the visible uplift began, subtle changes in gravity had been recorded by satellite instruments. The region's gravitational field weakened slightly, enough to suggest that mass within the crust had shifted upward. That observation supported the idea of fluids migrating through rock. The Earth, like a living organism, moves its fluids to maintain balance. These deep waters are not like groundwater. They are superheated and mineral-rich, capable of altering the density and strength of rock. When they move, they can turn solid layers into soft zones that deform rather than fracture. The coast's rise could be a symptom of this slow hydraulic breathing. Why should anyone care about a few centimeters of motion in a remote bay? Because this kind of behavior challenges the models we use to forecast earthquakes. Traditional models assume stress accumulates steadily until a break occurs. But if parts of the crust can deform gently, transferring energy sideways or downward, then the timing of those breaks becomes far harder to predict. It means the Earth has more ways to release tension than we thought. It also means there may be silent precursors to major quakes that instruments can detect if we learn what to look for. The lesson hides in the contrast between noise and signal. A massive earthquake announces itself with violence. A slow deformation whispers. We have long been trained to respond to the loud, but the planet often warns us softly. The challenge is not hearing the whisper, but believing it. The quiet coast was a whisper repeated over years, long enough that some researchers stopped calling it an anomaly and started calling it a process. From a human point of view, the process is nearly invisible. Houses do not tilt overnight. Roads stay smooth. The horizon remains flat, yet the cumulative shift changes everything about the local ecology. Streams reroute. Salt water intrudes farther inland. Vegetation lines retreat. Even the acoustics of a bay can alter as the seafloor rises. The coast is rewriting itself in units too small for a lifetime to grasp, but too large to ignore. And still, most people who live there will never feel the movement, only its effects. Beneath the technical findings lies a philosophical echo. The stability we rely on is itself a kind of illusion, a temporary pause in the endless negotiation of forces beneath us. The rift beneath the quiet coast is not a wound, it is an opening, a reminder that the solid Earth is anything but static. Every measurement we make is a snapshot of a breathing world, a freeze frame in a slow-motion dance that began billions of years ago and has not yet stopped. In one striking study, researchers modeled what would happen if the uplift continued. Within a century, the coastline could move inland by hundreds of meters. New wetlands would form where sea once lay, and rivers would carve new deltas. The change would not destroy civilization, but quietly redraw its boundaries. What seems eternal, like the line between land and water, is only a temporary truce. It is worth remembering that some of the most dramatic geological events in history began with years of gentle motion, before certain great eruptions. The land lifted slowly, tilting lakes and cracking roads. Warnings ignored because they were too gradual to seem urgent. The quiet coast may be another prelude, or it may simply be part of the planet's maintenance routine. Either way, it reminds us that the Earth does not owe us a steady floor. The pattern of uplift and sinking is now monitored daily by satellite constellations, ground sensors, and tide gauges. What used to take months to confirm can now be seen almost in real time. The more we look, the more similar patterns appear elsewhere. Coasts rise and fall like slow tides in the crust. The planet seems to pulse, and with each pulse we learn how interconnected its organs are. Land, sea, and mantle move in concert, transferring energy along paths we are only beginning to map. In everyday language, the world beneath us is restless, and its restlessness is part of what keeps it alive. The quiet coast is a living line where the crust flexes instead of breaking, where strain finds release through motion rather than catastrophe. The same physics that lets mountains grow allows valleys to sink, and both are part of the planet's breathing. We can measure it, model it, and name it, but we cannot stop it. What we can do is listen closely enough to recognize when the tone changes. And that tone is changing. The latest data show that the uplift has slowed, but the inland subsidence has deepened. It is as if the hinge has shifted farther under the continent, pulling new regions into the pattern. Perhaps the Earth is still adjusting, Or perhaps it is preparing for a larger rearrangement. Either way, the conversation beneath the coast continues, quiet but insistent. The sea may appear still, the village is unchanged, the horizon serene, but the planet beneath them is writing a story in motion, a story that connects to the signals we traced before. The same forces that send rings through the atmosphere are at work here, reshaping continents in silence. And as the coast breathes in, the next mystery rises inland, where orbs of light appear where they should not exist. It begins, as many mysteries do, with an ordinary witness. A pilot cruising above the clouds sees a sphere of light drift past the cockpit window, silent and smooth. It is no larger than a basketball, yet it holds its shape, its glow steady even as it slips across air dense with static. The crew notes no turbulence, no thunderstorm nearby, only the faint scent of ozone in the filtered air. When they land, the instruments show nothing. No spike in current, no interference. The orb was never there, at least not according to the machines. Reports like this are rare, but not new. For centuries, people have spoken of lights that appear during storms, rolling along fences or drifting through windows, glowing like captive suns. In earlier times, they were treated as omens, fragments of lightning trapped in spheres. In the modern age, science calls them by a colder name, ball lightning. Yet even that label hides ignorance. What exactly these orbs are, no one can yet say. In the laboratory, physicists have tried to summon them. They pass electric arcs through air, through silicon dust, through water vapor, hoping to coax a stable sphere of plasma into being. Most experiments fail. Those that succeed last only fractions of a second, flickering like a thought before vanishing. The few that persist longer offer hints rather than answers. Spectrometers catch traces of silicon, calcium, and iron, suggesting that the light feeds on vaporized dust. Cameras show a glow that expands and contracts as if breathing, but nothing explains how these spheres hold together or why they move with purpose, gliding as though guided by invisible strings. At its core, this is a study of defiance. Lightning should obey the rules of diffusion, spreading its charge until it fades, yet these orbs refuse to disperse. They twist, divide, sometimes pass through glass without breaking it. There are credible reports of them entering aircraft cabins, floating past startled passengers, then vanishing with a soft pop. Their lifetimes range from seconds to minutes, too long for conventional plasma, too short for any stable structure. Some scientists suspect a chemical reaction inside a shell of ionized air. Others propose exotic possibilities: microwave interference trapped by its own reflection, or quantum coherence at a macroscopic scale. Each idea solves one puzzle and opens another. In plain terms, these glowing orbs break more rules than they follow, and every attempt to cage them teaches us more about the limits of our understanding than about the lights themselves. They show that even in the most studied domain of physics, there are corners still in shadow. The world still holds surprises that make the instruments doubt themselves. The paradox becomes sharper when you consider where these lights tend to appear. They favor places where energy changes state the tops of storms, the edges of faults, the skin of water hit by lightning. They seem drawn to boundaries, to moments when nature is undecided. This pattern suggests that the orbs may not be entities at all but events, the visible part of a transition from one form of energy to another. A lightning bolt delivers raw charge to the ground. Sometimes that charge lingers, trapped in a pocket of vaporized material, shaping itself into something transient and nearly alive. A storm becomes a crucible, and the result is a light that should not exist. Witnesses describe them with eerie consistency. They hover, they move against the wind, they change color from white to orange to violet. Some vanish noiselessly, others explode with a sharp crack. One scientist who studied the phenomenon for decades called them fire behaving as if it had memory. That phrase captures both their elegance and their threat. Ball lightning has been known to burn holes in walls, scorch metal, and in rare cases, cause injury. But more often it leaves no mark at all, as if it were light without heat, information without source. Why does that matter? Because understanding these lights could bridge gaps between disciplines that rarely speak. They touch on atmospheric electricity, quantum plasmas, and the chemistry of aerosols. They force us to consider that some forms of energy may organize themselves spontaneously, defying our tidy categories. If light can act like matter, and matter like light, then our models of stability may need rewriting. In one remarkable incident, an orb appeared inside a research aircraft flying near a thunderstorm. The crew watched it slide along the aisle, bouncing gently as though cushioned by invisible hands. It passed through a metal bulkhead, leaving no damage. When investigators later analyzed the onboard sensors, they found a brief spike in radio frequencies but no current flow, whatever the sphere was. It had interacted with the instruments without touching them. Some proposed it was a kind of microwave cavity, a bubble of electromagnetic resonance formed by the aircraft's own systems. Others believed it was a plasma knot sustained by silicon vapor. None could prove it. Simply put, we may be seeing fragments of a language written in energy, messages the Earth sends when electricity and atmosphere collide under rare conditions. The orbs might be local self-organizing systems, balancing energy the way whirlpools balance flow. They appear where tension needs release, but not destruction. Like the ring in the sky or the rising coast, they represent nature's preference for transition over fracture. To test this, researchers built miniature storm chambers, filling them with humid air and dust. When they fired electric arcs, they sometimes produced tiny glowing spheres that drifted like their wild counterparts. High-speed footage showed that these spheres were hollow shells, thin membranes of plasma surrounding cooler gas. They survived longer when silicon particles were present, suggesting a role for solid matter in stabilizing the field. The discovery was modest but crucial. These lights were not illusions. They were real, measurable phenomena, hinting at a process the planet might use on larger scales. Why it matters reaches beyond curiosity. The physics of stability under extreme conditions informs everything from fusion reactors to spacecraft shielding. If a sphere of plasma can maintain structure in air, perhaps energy can be contained more efficiently than we thought. Studying these orbs might one day help us store power safely or understand lightning's role in the chemistry of life. The same principles that allow light to shape itself could explain how matter first organized on the early Earth, when the sky was alive with storms and the sea boiled with charge. Some researchers see in these spheres a metaphor for the planet itself. Energy constrained by its own fields, glowing but fragile, surviving only while balance holds. It is an unsettling analogy, yet fitting. Like ball lightning, civilization floats in a thin layer of air, shaped by forces it can measure but not command. We persist by equilibrium, not dominance. The mystery deepens with data from satellites. Instruments have detected brief bursts of light above thunderstorms, known as sprites and elves. These are not the same as ball lightning, but they share an uncanny geometry, glowing structures that form and vanish in microseconds, too high for aircraft, too fleeting for the eye. They are the sky's own punctuation marks, proof that electricity behaves artistically when it can. Perhaps the orbs below are echoes of these flashes, drops of the upper atmosphere's grammar falling to Earth. At night, near certain coasts and mountain valleys, witnesses report orbs that appear without storms, drifting like lanterns over ridges or hovering above rivers. Some correlate with seismic activity, leading to another hypothesis that piezoelectric effects in stressed rock release charge that forms luminous globes. If true, these lights could serve as silent warnings of pressure building deep below. Nature may have built an alarm system we have yet to decipher. For all its strangeness, the phenomenon reminds us of a recurring truth. Complexity does not always mean chaos. The lights are transient but patterned. They teach us that the boundary between known and unknown is not a wall, but a gradient. Each observation extends that gradient a little further into understanding. Even so, many scientists prefer to treat the topic with caution. It sits too near folklore for comfort, too close to the line where data thins and imagination thickens. Yet progress often begins in those uncertain spaces. There is something humbling in the idea that our planet still surprises us with basic displays of physics. We have mapped the orbits of planets, photographed black holes, split atoms, and still cannot explain a ball of light that floats across a field. The humility is not weakness. It is a form of respect, a reminder that the unknown is not an enemy, but a horizon. If a storm can birth light that behaves like thought, what else might emerge from energy given the right constraints? Could intelligence itself be a kind of persistent plasma, an organized glow of charge held together by balance and feedback? The idea sounds poetic, yet it points to the same principle the orbs reveal, that order is not an accident, but a property that matter seeks under tension. The next chapter of our journey will follow this pattern of unlikely cohesion into another realm. The coast has lifted, the air has spoken in rings, and now light has learned to hold shape where it should not. But fire does not always need the sky. Sometimes it burns cold, across a continent, under a shroud of smoke. The next door opens where flame becomes climate, and we enter the cold flame of a continent. The first sparks are invisible. They rise from parched grass under a dry electric sky, from twigs that have forgotten what rain feels like, from the friction of wind dragging over bark and stone. One spark finds fuel, then another, within minutes. Heat builds not as a line, but as a column. The air itself begins to rise, pulling oxygen upward in spirals. What began as a local fire becomes a structure, a living column of smoke and lightning. Satellites catch at first a towering plume climbing higher than most storms. Meteorologists give it a name that sounds contradictory: a pyrocumulonimbus cloud, a storm made by fire. From orbit, the image is haunting: a continent the color of rust, traced by veins of smoke that stretch hundreds of kilometers. Pockets of flame flash like cities on a dark map. The column at the center glows at its base with molten red, while its crown spreads wide and gray, cold to the touch of instruments but alive with charge. Lightning forks within the plume, not from cloud to ground but within the ash itself. It is as if the continent has built its own weather system, one born from combustion rather than sunlight. The paradox sits in plain sight. Fire should consume oxygen and die. Yet these fires create air currents strong enough to build storms that feed them. They cool the upper atmosphere while heating the ground, forging a circulation pattern that defies common sense. When the column reaches the stratosphere, the smoke spreads for thousands of kilometers, circling the planet like ink in water. Sunlight dims slightly for weeks. The planet's heartbeat, measured by temperature and wind, stumbles for a moment. What we call the cold flame is this strange inversion fire that cools the world even as it burns it. In plain terms, a pyrocumulonimbus is a feedback loop between combustion and weather. The heat from massive fires lifts smoke into the upper air. There, particles act as nuclei for ice, generating lightning that can ignite new fires below. The system feeds itself until fuel or atmosphere runs out. In recent decades, these events have grown larger, merging across regions to form what scientists now call pyroconvective complexes. One of them can produce the same electrical energy as a mid-sized thunderstorm. The difference is that these storms do not rain to extinguish their source. They rain embers. Witnesses on the ground describe the experience as apocalyptic. The sky darkens at noon. The air tastes of metal. Birds vanish. Flames advance not in lines but in waves, skipping across treetops faster than people can run. In the center of the storm, the heat is so intense that soil minerals melt and fuse into glass. The The ground hums with static. A photographer once caught an image of lightning threading through a curtain of smoke, each bolt green at the core. The color came from vaporized copper carried by wind from burning infrastructure. Civilization itself had become fuel. Why does this matter? Because these events are not anomalies. They are experiments the planet is conducting with our participation. Every vast fire injects millions of tons of aerosols into the sky. Some reflect sunlight, briefly cooling the surface. Others absorb heat, altering circulation patterns. These plumes can cross oceans, turning sunsets crimson thousands of kilometers away. The Earth has always burned, but never before with this frequency or reach. The line between natural and engineered fire has blurred. The cold flame teaches us something profound about energy. It shows that systems can reach points where the feedback itself becomes the main driver. The more the fire burns, the more wind it creates, and the more fuel it draws in. This runaway cycle mirrors the dynamics of many human processes, economies that grow until they overheat, technologies that accelerate beyond control. Fire is not only a phenomenon of chemistry, it is a metaphor for imbalance. What begins as a tool can become a climate. There is a kind of terrible beauty in these storms. From a distance, their anvil tops glow under the sun like sculpted marble. Jet pilots describe them as towers of smoke rising above weather fronts. Smooth on top, boiling below. The lightning inside flashes white, then violet, illuminating shapes that look like cathedrals. For a moment, the spectacle steals breath, until one remembers what it is made of: forests, homes, animals, memories, all transmuted into heat and ash. Each flash of light is a record of something that once lived. At its heart, fire is transformation. Matter turns to gas, carbon to carbon dioxide, potential to entropy. But when the scale reaches that of a continent, transformation becomes broadcast. The cold flame announces that human and planetary systems are now intertwined beyond separation. Our industrial heat and the planet's natural cycles have fused into one experiment. When we light a field, the atmosphere answers. When the atmosphere changes, the field burns faster next time. Cause and effect have folded together. In everyday language, we are watching the atmosphere become a memory of fire. The smoke that lingers high above acts as a diary of combustion, a layer of gray script recording the temperature and intensity of each blaze. Scientists read these entries through instruments that analyze light scattering. They can tell where the smoke came from, how high it climbed, even how much metal it carried. What the measurements reveal is both comforting and alarming. The system is consistent, the math works, but the consistency means the process can repeat easily. The planet has learned how to make these storms. People who live near fire-prone regions understand this instinctively. They prepare go bags each summer, check wind directions, track satellite images on phones. They have learned to read the sky not as backdrop but as forecast. When the horizon turns copper at noon, they know what comes next. Yet there is something new in recent years. A tone of fatigue. Fires that once came once a decade now arrive every few seasons. The rhythm of rebuilding has become part of life. The cold flame no longer shocks. It recurs. The science behind the glow is elegant even as the scene is grim. As smoke rises, it cools and expands. Water vapor within condenses into ice crystals, which collide and build charge. When the difference between regions of the cloud becomes great enough, a spark leaps, lightning born from the friction of frozen ash. The process mirrors that of ordinary thunderstorms, but with one inversion: the heat source is below, not above. That inversion explains why these storms rarely produce rain. They are too warm from the bottom to complete the cycle. In effect, they are engines with no brakes. From space, the aftermath of one such storm looks like a bruise on the planet. Satellites detect a broad region where sunlight bounces differently, dulled by particles that drift for weeks. The optical thickness changes the color of the sky, making sunsets blood red. Temperature readings drop slightly, a ghost of volcanic cooling but shorter-lived. The irony is sharp. A disaster that raises global carbon levels also casts a brief, false shade that cools the surface. It is the climate's dark sense of humor, a gesture of balance that fools no one. To put it another way, the cold flame is the mirror of our own industry. Both burn carbon, both alter air, both leave residues that rewrite the weather. The fires may seem wild, but they are in conversation with our factories, our power plants, our vehicles. Every particle of soot that rises joins a dialogue about the future composition of the air. In that dialogue, each side answers the other. We are speaking to ourselves through the medium of smoke. Why it matters extends beyond immediate destruction. These towering fires pump their emissions higher than normal pollution, where winds can carry them across hemispheres. They influence jet stream patterns, shifting rain belts and feeding droughts elsewhere. The consequences do not stop when the last ember dies. They travel, settle, and seed new outcomes. Fire, once local, has become a global participant. Each plume is a messenger that says nothing stays where it starts. There is a line in a field report from a firefighter who watched such a storm from a ridge. "The fire was making its own weather, and we were just passengers," he wrote. That sentence captures the scale of the shift. Humans, who once controlled flame with flint and water, now find themselves at the mercy of versions they cannot contain. We have taught the atmosphere to burn, and it remembers the lesson. The smoke columns have other effects. In the upper stratosphere, soot absorbs sunlight and warms the surrounding air, altering the chemistry that protects us from ultraviolet radiation. These interactions are subtle but real, measurable in the slow depletion of ozone after major fire seasons. The cold flame, therefore, is not only a symptom, but a catalyst, a feedback that links the smallest spark to the integrity of the sky. Still, amid all this destruction, there is one glimmer of adaptation. Forest ecologists note that some seeds require fire to open. Certain pines depend on heat to release their future. When the flames pass, the ground cools, and within weeks the first shoots appear, green against black. Life rehearses resilience even as it suffers. The pattern is ancient: burn, renew, adapt. The question now is whether the same rule can apply to civilization. Our cities are built on the same materials that feed the cold flame: carbon, metal, energy. They too can ignite metaphorically and physically. The balance we seek lies in redesign, not retreat. Fire, in its cold form, reminds us of what we have borrowed from the planet's chemistry and what we risk if we forget repayment. A storm born of fire is a sermon about limits. As the smoke drifts across oceans, satellites continue to track its path. The gray plumes merge with weather systems far away, dimming the light over seas that have never seen the original flames. Fishermen in distant waters notice redder dawns, unaware they are watching the residue of another continent's disaster. The circle closes: heat in one hemisphere becomes haze in another. Energy has no borders. When the last ash settles, the land bears scars that resemble river deltas viewed from above, branches of black spreading outward from a single spark. To some, it looks like death. To others, it looks like pattern, the signature of a system seeking equilibrium. Either way, it is evidence that the world remembers its fires longer than we do. The cold flame is not finished with us. The next chapter follows its trail upward, into the realm of stars that burn for reasons not our own. For if the earth can summon storms from its own skin, what then of suns that die and scatter flame across the void? The journey continues with fire from distant suns. Night falls, and the sky blooms with quiet fire. Each star appears small, a pin of light against endless black, but every one of them is a furnace. A single grain of their heat could outshine all our cities. We live under a field of suns, each at a different stage of its long burning. Most seem remote and harmless, but sometimes their fire reaches us across light years, not as warmth but as radiation, and not as comfort, but as memory. The universe is full of explosions that have already happened, and their echoes fill our sky. The death of a star is not an instant. It is a conversation between gravity and pressure, a slow argument that ends when the fuel is gone. When gravity wins, the collapse begins, and the balance that held for millions of years breaks in seconds. In that brief release, the star becomes something new, a supernova, the most efficient way matter knows to end itself. For days, it shines brighter than a whole galaxy. For months, it leaves behind a fading ghost of light. For millennia, its debris drifts outward, seeding the galaxy with the heavy elements that build planets, oceans, and blood. Everything we touch was once inside a dying star. In plain terms, when a massive star runs out of fuel, it cannot hold back its own weight. The outer layers fall inward, then rebound with unimaginable force, creating a shockwave that tears the star apart. The explosion throws atoms into space at a fraction of light speed. In its core, under pressures so high that even atoms cannot survive, a neutron star, or a black hole, forms. The process is violent but also creative. Without these deaths, there would be no gold in rings, no calcium in bones, no iron in our blood. The fire that ends a star is the reason we exist to watch it. Astronomers have cataloged thousands of these events, but only a few have left marks close enough to matter for us. The fossil traces of nearby supernovae lie hidden in ocean sediments and lunar dust. They contain rare isotopes, like iron-60, that can only form in the heart of an exploding star. When these atoms show up on Earth, they serve as postcards from a cosmic disaster millions of years old. One such layer in our seabed suggests that a supernova went off about 2.5 million years ago, close enough to expose the planet to a wave of radiation. The effect may have thinned the ozone layer and altered climates. Some researchers even speculate it influenced the evolution of early humans, nudging ecosystems toward change through subtle environmental pressure. It is an unsettling idea that a flash of light across the galaxy might have steered the path of life here. The paradox is that such violence can also protect. Cosmic rays from supernovae help regulate the chemistry of interstellar clouds, preventing them from collapsing too fast. In this sense, the explosions are part of the breathing of galaxies, their way of maintaining rhythm. When stars die, they stir the medium from which new stars will form. Creation depends on destruction. It always has. Even the radiation that seems hostile carries the seeds of renewal. Our instruments let us see these fires with astonishing precision. Telescopes record the fading light curves of supernovae, mapping how the energy dissipates. Spectroscopes break the light into bands that reveal the elements being forged. Each spectrum is a signature, a fingerprint of the dying star. When astronomers saw one with double peaks where there should have been one, they realized they were witnessing two stars merging before the explosion. The universe was not only killing, it was sculpting. The data showed us that stars are social creatures, living and dying in pairs, trios, even clusters, their fates entangled like notes in a cosmic chord. There are rarer deaths, stranger and harder to imagine. Some stars collapse not into neutron stars, but into black holes so dense that light itself cannot escape. Around them, matter spirals inward, heating to billions of degrees. From these accretion disks shoot jets that can extend thousands of light years. Beams of radiation so focused they could sterilize planets in their path. When these jets point toward us, we see them as gamma-ray bursts, the brightest events in the known universe. One such burst, if close enough, could strip our atmosphere within seconds. Fortunately, the cosmos is vast, and those beams usually miss us. Yet they remind us how fragile safety is, and how narrow the corridor of habitability can be in a universe built from explosions. Why does this matter? Because understanding these stellar deaths is not just astronomy, it is self-awareness on a cosmic scale. Every atom heavier than helium in our bodies comes from such events. Each breath contains traces of stars long gone. When we study supernovae, we are studying our own ancestry. But we are also mapping our vulnerabilities. The same radiation that made the elements we depend on could, under different geometry, unmake the balance that allows life to endure. To put it another way, stars are both builders and erasers. They write in heat and pressure, and they edit with radiation. Life exists in the margin between their generosity and their indifference. We live in that narrow space where sunlight warms but does not burn, where cosmic rays fertilize but do not fry. Our planet's magnetic field and atmosphere act as filters, tuning the universe's violence into a manageable background hum. It is a fragile arrangement, and every study of distant suns reminds us that it is temporary. Astronomers once thought the Milky Way was a quiet neighborhood. That illusion faded when they began to map remnants of past explosions. The sky is littered with expanding shells of gas, remnants of stars that died before humanity existed. Some still emit in radio and X-ray, echoing across space like cosmic fossils. When viewed in composite, the galaxy resembles a field after harvest, scattered with burned circles where giants once stood. Even in apparent peace, there is constant renewal. Stars form from gas enriched by earlier deaths, and the cycle continues. Our sun, modest and stable, was born from such material about 5 billion years ago. It carries in its chemistry the fingerprints of countless earlier catastrophes. For now, we orbit a mild star, but cosmic scale has no sentiment. One day, our sun will exhaust its hydrogen and expand into a red giant. The inner planets will be swallowed, their rocks vaporized into plasma. Earth's oceans will boil away long before that, leaving only a glowing core. Billions of years later, what remains of the sun will shrink into a white dwarf, a cinder the size of Earth but a million times denser. It will shine faintly for trillions of years before cooling into darkness. The end is not tomorrow, but it is written. In everyday language, the stars are telling us a story of patience. Their timelines dwarf ours, yet their lessons are immediate. They remind us that nothing stable lasts forever, that balance is always temporary, and that the energy we take for granted is borrowed, not owned. To study them is to learn humility in units of light years. Among the most remarkable discoveries of recent decades is that nearby supernovae leave traces not only in rocks, but in biology. Tiny magnetic crystals found in certain bacteria align with fields influenced by cosmic radiation. These organisms may have adapted in part to increased radiation from long-ago stellar events. If so, then life on Earth is already intertwined with the rhythm of galactic death and rebirth. The galaxy is not a stage for life. It is part of its mechanism. Another curiosity lies in how these distant fires sculpt the future beyond our reach. Supernovae compress nearby gas clouds, triggering new waves of star formation. The light that destroys one world may kindle another. A chain reaction of creation travels through the galaxy like a slow tide. Somewhere, right now, the elements from one star's death are forming the crust of a newborn planet. Perhaps another intelligence will one day look up at their sky and wonder about us, unaware that our atoms and theirs are cousins. Human imagination has always looked upward for omens. Ancient civilizations tracked supernovae as celestial portents, carving records of strange new stars that appeared and faded. In those carvings, we see ourselves reflected curious, fearful, persistent. The cosmos has not grown less mysterious since then, only more measurable. We have replaced superstition with data, but awe remains, unchanged and essential. There is comfort in knowing that the universe is consistent even in its chaos. The equations that describe stellar death are the same ones that keep our lights on. The difference is only scale. Fusion and fission, collapse and release, balance and breach, these are universal. Every flickering candle echoes a star's final breath. Every heartbeat is a tiny negotiation between energy and gravity. The fires from distant suns still reach us, filtered by distance and time, reminders that our safety depends on their restraint. We watch them with telescopes that catch photons older than our species, and we call it observation. But it is also listening, a way of hearing across eras. The next flash we detect might be a warning or a gift, depending on where we stand when it arrives. And so the chain continues. From the cold flame of a continent to the fire of distant suns, energy moves through scale after scale, linking forest to galaxy, ember to star. Yet one fire still waits closer to home, hidden within the star we know best. The next chapter will follow its reach and ask what happens when the sun itself decides to knock. It begins without light, no flare, no blinding flash, just a sudden tightening of invisible fields that stretch between the sun and earth like threads. Deep within the sun's atmosphere, a tangle of magnetic lines twists on itself, storing tension until it can no longer hold. The knot snaps, and a vast cloud of charged particles explodes outward. Astronomers call it a coronal mass ejection, or CME. It is not fire in the human sense, but a storm of plasma. Atoms stripped of electrons, carrying electric currents and magnetic fields across millions of kilometers of space. It travels faster than any wind on Earth, silent and relentless. 3 days later, the wave reaches us. The first warning comes from satellites stationed between the planets. They feel the approaching storm before the ground does. Their instruments show a sudden rise in proton flux, the signal of an incoming shock front. Space weather centers issue alerts, predicting auroras at latitudes that never see them. People imagine shimmering skies and colored lights, not realizing that beneath those lights, electric currents are already crawling through the bones of the planet. When the wave hits the magnetosphere, Earth responds like a drum struck by an unseen hand. The planet's magnetic shield compresses on the daylight side and stretches on the night side. Energy is dumped into the upper atmosphere, driving vast currents that race along field lines toward the poles. There, the energy becomes light, green and red curtains rippling across the sky. The aurora is beautiful, but beauty hides scale. The same flow of charge that paints the heavens induces electric fields at the surface. Long metal structures, like pipelines and power lines, become unintended antennas. Currents surge through them, invisible but potent. In the right conditions, they can melt the cores of transformers or overload circuits built for calmer skies. In plain terms, a geomagnetic storm is the sun's way of reminding us that our world is still plugged into its field. Electricity, which we think of as ours, is a borrowed art. The sun can write across it at will. The Great Storm of 1859, remembered as the Carrington event, proved that even in a simpler era, the consequences could be global. Telegraph wires sparked, paper caught fire. Operators received shocks through keys that were supposed to send dots and dashes, not lightning. For 2 days, auroras glowed over the Caribbean. Compasses spun in circles. The sun had knocked, and the door was open. Modern civilization is more vulnerable, not less. Every satellite, every grid, every GPS receiver sits inside this magnetic cage. A storm large enough to disturb the field could disable navigation systems, disrupt communications, and fry transformers that take years to replace. The risk is not hypothetical. In March 1989, a geomagnetic storm caused the electrical grid in Quebec to collapse within 90 seconds. 6 million people lost power. The lights of the north flickered, then died. Engineers traced the cause to induced currents that saturated transformers until they shut down. The event was a faint echo of Carrington's, but it was enough to show how thin the line of control had become. To understand why, picture the Earth's magnetosphere as a bubble moving through a solar wind. Under normal conditions, this wind is steady, pressing gently against the magnetic field like a constant breeze. During a CME, the wind becomes a gale, loaded with its own magnetic polarity. When that polarity opposes Earth's, The fields connect directly, allowing energy to pour in. The bubble breathes inward, then snaps back, releasing currents through the ionosphere. The faster the solar wind, the deeper the impact. Some storms last minutes, others resonate for days. What we call weather in space is not metaphor. It is real, measurable, and dangerously energetic. Why does this matter? Because our dependence on electricity is absolute. Transformers are heavy and custom-built, requiring months or years to replace. In a global storm, hundreds could fail at once, each a link in the chain of generation and distribution. Even regions untouched by the direct blast would feel the loss through supply shortages, communication breakdowns, and economic aftershocks. The world would not end, but it would stumble in ways we are not prepared to catch. Scientists try to map the thresholds. They measure how much voltage different systems can tolerate, how much induced current a transformer can carry before its core saturates. They run simulations of storms larger than any recorded, learning how quickly cascades would spread. The numbers are sobering. A Carrington-level event today could leave entire regions dark for months. The damage would not come from heat or radiation, but from imbalance. The same kind of feedback that drives a wildfire or a financial crash. When energy moves faster than a system can redistribute it, failure propagates. There is poetry in this danger. The same star that sustains life also holds the power to pause it. Sunlight grows our crops, charges our panels, and defines our rhythms. Yet its storms remind us that energy is not gift, but relationship. The sun is not malevolent. It is indifferent, a continuous machine of fusion whose cycles follow physics, not mercy. Our task is not to plead with it, but to learn its timing, to prepare for its moods as sailors prepare for the sea. In everyday language, the sun's storms are space's equivalent of weather fronts. They rise from regions of complex magnetism, often near sunspots. These dark patches are cooler on the surface, but harbor fields twisted into knots. When those knots snap, energy is released in bursts of light called flares and in massive plasma eruptions. We can see the flares instantly, but the plasma takes time to arrive. Like thunder following lightning, between the flash and the impact lies the window of warning. Space agencies track this interval obsessively, issuing forecasts hours before the wave reaches us. Yet even with that warning, protection is imperfect. We cannot shut off the grid. We can only try to absorb the blow. The auroras that accompany such storms are among the most beautiful sights nature offers. Curtains of light ripple in silence, shifting from green to red to violet. People step outside to watch, unaware that what dazzles their eyes may also be straining the circuits that keep their homes lit. Beauty and danger coexist in the same moment, the same current. Some traditions see the aurora as the dance of spirits. In a way, they are right. These lights are the visible breath of a planet responding to its star. The scale of a solar storm's reach extends far beyond Earth. Astronauts aboard spacecraft are particularly vulnerable. Without the protection of the atmosphere, a strong solar event could deliver lethal doses of radiation in hours. Missions to the Moon and Mars must time their trajectories to avoid these flares. The challenge is partly technical, partly philosophical. How to live in a universe where the environment can change faster than warning can travel. To put it another way, our solar system is not a stable playground. It is a dynamic system of fields and flows, and Earth rides within them like a charged particle in a circuit. The sun is the source. The planets are resistors, and the vacuum between them is the conductor. Every storm is a surge. Every aurora is a current displayed in light. When we build technology that uses electricity, we extend this circuit into our own creations, making them part of the solar machine. The danger is not that the sun will notice us, but that it already includes us in its design. Some scientists have begun to propose new shields for satellites, artificial magnetic bubbles that could deflect the worst of the plasma. Others are working on transformer designs that can ride out geomagnetic currents without failure. Progress is real but slow, because the problem lies not only in materials but in imagination. We are still learning to think in scales that match our star. For centuries, humanity treated the sun as symbol, then as source. Only recently have we begun to see it as a neighbor with moods. The story of solar storms carries another paradox. They can harm, but they also teach. By studying how the magnetosphere responds, scientists learn how energy moves through plasmas, knowledge that may one day help contain fusion on Earth. The sun becomes both threat and teacher. It demonstrates stability achieved through motion, equilibrium maintained by flux. If we can mirror that principle, our own energy systems might gain resilience rather than fragility. Why it matters reaches beyond technology. The sun's behavior shapes not only our machines, but our sense of time. Its cycles of activity, roughly 11 years long, influence climate, radio propagation, and even the rhythm of human attention. Civilizations once counted these cycles through sunspots, predicting harvests and omens. Today we count them through satellite telemetry. But the intuition remains the same. The sun breathes, and we must breathe with it. When a strong storm arrives, we see its signatures everywhere. Power companies watch voltmeters quiver. Airlines reroute flights away from polar routes where communication can fail. Radio operators listen as static floods the bands. Even animals react. Pigeons lose their bearings, whales alter their migrations, and certain species of bacteria slow their growth. The storm writes its presence across every level of life, from ionosphere to ocean floor. It is a reminder that we are not isolated but immersed. If a Carrington-level event struck today, the night sky might glow as bright as dawn. People would step outside in awe, phones dead, screens dark, the air alive with static. For a few hours, the world would feel ancient again, illuminated only by fire and sky. Then the reckoning would begin, the slow restoration of grids, the rebuilding of satellites, the relearning of patience. In that silence, we might remember what the lights in the heavens always meant, that power and fragility are twins, and that the sun's voice, however distant, can still be heard. For more evidence-driven insights, like and subscribe to the Quiet Universe channel. The next pulse in our journey follows not the sky, but the ground, tracing the ledger of carbon and steel that binds civilization to the energy of its star. Beneath the surface of every city lies a hidden book. It is not written in ink or stored in code, but in concrete, metal, and air. Every bridge, every beam, every spark that lights a room is a line in that ledger. The entries are made in carbon and steel, balanced by the currency of heat. To walk through a metropolis is to turn the pages of that book, tracing the invisible debts we owe to the planet's chemistry. Civilization, for all its grace, is a transaction between fire and matter, and every transaction leaves residue. The story of that residue begins deep in the crust. Iron ore waits in seams that glitter when broken, a dull red that only reveals its worth under flame. To pull iron from stone, we must reverse the work of time. The ore must be smelted, oxygen stripped away, carbon added to strengthen the metal. That carbon once lived as gas, drawn from the air into plants, trapped in coal, oil, or limestone. We free it again to forge steel, returning to the atmosphere what the Earth had hidden. Every ton of steel carries a shadow of carbon dioxide, a ghost exhaled in the making. The stronger the material, the deeper the breath. In plain terms, steel is made by combining iron with carbon at high heat, usually above 1500 degrees Celsius. That heat does not come freely. It demands fuel coke from coal, gas from wells, electricity from power plants, each step an exchange of stored energy for structure. The result is the skeleton of our civilization, resilient yet fragile in origin. Every skyscraper, bridge, and ship is a testament to our mastery of energy, and a reminder of its cost. Factories hum with that bargain. Blast furnaces roar like captured volcanoes, their interiors glowing orange, lined with refractory brick that lasts only months before it too must be replaced. conveyor belts feed them with iron, lime, and coal. Molten metal pours into molds, hissing like waterfalls of light. It is easy to be awed by the precision, to forget the price paid in invisible gases drifting upward. Inside the glow is the same reaction that once built the planet's first atmosphere, carbon meeting oxygen, releasing heat, giving structure, and writing debt. Why does it matter? Because steel and carbon are not just materials, they are mirrors of our relationship with energy. Steel gives us strength, but its creation consumes the very element that destabilizes our climate. Carbon fuels our progress and at the same time measures our excess. Together they form the double entry accounting of modernity, what we gain in infrastructure, we pay for in equilibrium. The ledger is always balanced, but not always in our favor. To put it another way, the planet keeps its own books. Volcanoes add carbon to the air, oceans remove it, forests store it in cellulose and root, over eons. This exchange kept temperatures within a range that allowed life to persist. Our industry has joined that cycle, adding new entries faster than the old ones can settle. The numbers are small by cosmic standards, but large by human ones. A single steel mill can release as much carbon each year as a small country. Multiply that by thousands, and the sky begins to change color. In everyday language, we are living in the age of smelters and chimneys, where progress is measured in tons and degrees. Yet even as we alter the atmosphere, we depend on the materials that cause the change. There is no city without concrete, no hospital without steel, no electricity without the carbon that once lay buried. The dilemma is not moral but physical. We are bound to the chemistry of our tools. The paradox deepens when we look closer at carbon itself. It is the element of life and of loss. It binds DNA, fuels respiration, and builds the lattice of diamonds. It also traps heat in the air and melts glaciers. The same atom that holds a leaf together can hold sunlight captive for centuries. We do not emit carbon as punishment or negligence. We emit it because it is the backbone of motion. Every car, every computer, every meal heated by flame is part of the same equation. The Earth has tolerated our accounting for centuries, but the balance is shifting. Inside the foundries, workers speak of steel as if it were alive. They listen to its tone when struck, judge its mood by its glow. A perfect ingot rings cleanly. A dull one sulks. These rituals belong to a craft older than writing. The forge is humanity's first laboratory, and the steelworker its first engineer. Yet the ancient art now carries planetary consequences. Each heat poured adds a trace to the sky. The plume from a modern mill can be seen from space, a gray signature that travels with the wind. Why it matters is more than climate arithmetic. The processes that built our world also define our vulnerabilities. A disruption in fuel supply can halt construction, transport, or food production. The same networks that feed our prosperity can fail together. In that sense, carbon and steel are not only materials but nerves, transmitting stress through the global body. When one line trembles, the vibration travels far. Scientists and engineers are searching for new balances. Some pursue hydrogen-based steelmaking, replacing coal with gas that emits only water. Others explore electrolysis, splitting oxides with renewable power. These experiments echo the early days of smelting, uncertain, dangerous, hopeful. Progress is slow because the scale is immense. A single furnace can produce thousands of tons per day. Replacing even one means rethinking the foundation of industry. Yet within those challenges lies an opportunity to rewrite the ledger, to change how we make the bones of our cities. The atmosphere records everything we do. Ice cores in polar regions preserve bubbles of ancient air, each layer a chapter of the Earth's climate. The most recent layers show a sudden spike in carbon dioxide, a signature that aligns perfectly with our industrial revolution. The line on the graph rises like the curve of a new skyscraper. Future scientists, if any exist, We'll be able to read our era in those bubbles, an age of steel and smoke, of heat and ambition. Whether they judge it as triumph or warning will depend on what we do next. To bring it closer, think of a single object, a bridge. It spans a river, connecting communities, saving lives, creating commerce. But to exist, it required mining, oil, transport, fuel, and heat. Its cost in carbon was paid long before the first car crossed it. The bridge is both miracle and message. It proves our ingenuity, and it marks our debt. The same can be said for every skyscraper, train, and turbine. They are all entries in the same planetary account. The ledger of carbon and steel does not end at the factory gate. The products it creates shape culture itself. Cities grow taller because steel allows it. Transportation accelerates because engines demand it. Our sense of time compresses because we can build faster. And with every acceleration, the ledger thickens. Energy invested becomes lifestyle, and lifestyle becomes expectation. To slow down feels like loss, even when speed erodes the balance we need to endure. Yet the future is not fixed. The same chemistry that traps heat can also store energy. Graphite batteries, carbon fibers, and new alloys show that the element story is not finished. We can teach it new behaviors, coax it into forms that support rather than consume. The key is not guilt, but design building systems that account for their own exhaust, materials that remember where they came from and where they will go. In that vision, the ledger still exists, but its entries grow lighter. One truth remains constant: we cannot erase the record. The carbon already in the air will linger for centuries, absorbed slowly by oceans and stone. The task now is to stop adding faster than the planet can write off the debt. That is less a call to renunciation than to intelligence. The next revolution will not be of abundance or austerity, but of precision, knowing exactly how much energy a thing requires and refusing to pay more than necessary. The final paradox of this chapter lies in perspective. From orbit, the world at night glows like a forge. Every city, a pocket of heat and light. The photograph is beautiful, but it is also an audit. Each point of light is powered by combustion, nuclear reaction, or chemical flow. Each dot is a declaration of existence and a reminder of cost. The map of civilization is the map of energy expenditure. As we read this ledger, we begin to see our role differently. We are not accountants balancing a distant budget, but authors deciding what kind of story to write. The numbers are physics, but the meaning is ours to assign. We can choose to continue burning pages faster than we write them, or we can learn to compose with restraint. And so the chapter closes where it began, in the glow of furnaces and the breath of smoke. The balance between carbon and steel defines the balance between progress and survival. The next part of our journey asks what happens when that balance fails. When supply chains fray and the world must start again from fragments. The door ahead opens into the possibility of reset, and into the question of what endures after the lights go out. It begins quietly, as collapses always do, not with an explosion or an apocalypse, but with the slow fading of hums. Screens flicker, machines pause, and a long silence settles over a world that once never slept. Cities become landscapes of still air and cooled steel. Elevators hang motionless in shafts. The wind carries no engines, only the soft pulse of the planet reclaiming its rhythm. Civilization, built on the choreography of electrons, meets its first still moment in centuries. After the reset, time itself seems to widen. People emerge from buildings blinking, hearing the unfiltered sound of birds and wind for the first time in years. The air feels heavier, not with smoke, but with unfamiliar quiet. It is as if the world has inhaled and forgotten how to exhale. Some look for answers in the sky, others in the ground. But the truth lies in both. The same systems that powered the world have turned inward, folded by their own complexity. The sun had knocked, the grids had faltered, and the chain of dependencies snapped link by link. What remains is continuity stripped to essentials: breath, water, and patience. To understand what happens after the reset, imagine peeling civilization back to its fundamentals. No network, no digital clock, no distant supply. The first hours are disbelief. The first days are improvisation. Hospitals turn to hand pumps and mechanical ventilators. Farmers measure time by shadow instead of screen. The stored food that once arrived by truck now sits in warm silence. The fragile symmetry between energy and need reveals its imbalance. Yet amid the disruption, something ancient stirs the instinct to adapt. In plain terms, a reset does not erase knowledge, but it pauses access to it. The data still exists on hard drives and in books, but without power, it becomes inert memory. Humanity must bridge the gap between what it knows and what it can still do. Some regions restart quickly, drawing from small solar arrays or local turbines. Others fall quiet for months. The world fractures into zones of light and shadow, each rediscovering the meaning of self-sufficiency. The age of convenience folds back into the age of endurance. Factories cool into monuments. Highways fill with still vehicles, their frames glinting under unfiltered stars. The night sky, free of electric haze, reveals itself in overwhelming clarity. Constellations unseen for generations blaze overhead, sharp and cold. For some, this is terror. For others, revelation. The stars, once symbolic, now provide navigation again. Time slows enough to be felt. Each hour, measured by the sun's arc or the sound of a river, gains weight. What was once background noise becomes the measure of survival. There is no single narrative for collapse. Some communities crumble, others reweave. On the edges of old cities, small enclaves find ways to restart the simplest machines: water wheels, wind turbines, radios powered by hand-crank generators. These humble devices become bridges between eras. Knowledge, like current, needs a circuit. The reset teaches that technology is not progress itself, but a medium for it. The real progress is learning how to rebuild, one loop at a time. Why does it matter? Because the reset is not an ending. It is a mirror. It reflects what was essential and what was ornamental. When systems fail, the hierarchy of need reveals itself with brutal honesty. Air before comfort, food before efficiency, connection before speed. The human web, stripped of artifice, becomes visible again. People barter skills, share warmth, reimagine the social contract. The world does not vanish. It becomes smaller, slower, and perhaps, briefly, wiser. The paradox is that in losing power, humanity gains clarity. Without the constant glow of devices, night returns as teacher. Firelight becomes both warmth and communication. Conversations lengthen. Children look upward instead of downward. Memory becomes oral again, passed by voice instead of signal. Yet this simplicity carries risk. Without the buffer of stored energy, every storm, every drought, every illness grows sharper. The planet's natural rhythms, once background, now dictate survival. Archaeologists of the future, should they exist, will find our era written in two layers, one of metal and glass, the other of silence. They will see how quickly complexity can vanish, how cities can turn to shells without the invisible scaffolding of current. But they may also find evidence of resilience: gardens planted in city squares, windmills resurrected from scrap, libraries reopened by candlelight. In the quiet, humanity remembers that knowledge itself does not burn easily. It waits for rediscovery. To put it another way, the reset is an audit of dependence. Every machine that fails marks a point where trust was placed outside ourselves. Every device that survives marks a lesson learned. People begin to map these lessons into new kinds of infrastructure: decentralized, modest, built to endure rather than to impress. Villages form microgrids powered by wind and water. Old hydro turbines are repaired and linked with salvaged electronics. Communication returns in fragments: shortwave radio, hand-carried messages, coded flashes of light. It is primitive only by comparison to what came before. In practice, it is elegant adaptation. In everyday language, this is what civilization looks like when it breathes differently. The rhythm of life aligns again with the planet's natural pulse. Crops follow the seasons, not global markets. Movement becomes intentional, not automatic. Energy use becomes a moral decision, weighed against cost and consequence. And slowly, the lights return, one cluster at a time, glowing not as dominance but as declaration: we are still here, and we have learned. Yet not everyone welcomes the return. Some cling to the memory of speed, mourning the silence as loss. They look at the stars and see only what has been taken. Others see the same sky and feel gratitude. They build new rituals around dawn and dusk, measuring wealth in hours of light. In this balance, a new culture forms, one that remembers both the fragility of grids and the persistence of hands. Why it matters lies in continuity. The reset reveals that civilization's true resource is not fuel, but imagination. Energy can vanish, but ingenuity endures. When the great networks fell, it was not engineers who vanished, but engineers who adapted. They rewired what remained, turning bicycles into generators, water wheels into microplants, sunlight into currency. The world, broken into fragments, still spoke the language of physics and patience. Somewhere, in what used to be an industrial valley, a group of survivors restarts a small furnace. They melt scrap metal into new tools. Sparks fly again in the dark, echoing the first forges of ancient times. The circle closes, but not perfectly. This time, knowledge precedes technology. They understand the chemistry of steel, the cost of carbon, the danger of overreach. They forge not for empire, but for endurance. Each tool made is a seed for recovery, each flame a rehearsal for a gentler kind of industry. The planet, too, begins its own restoration. With fewer emissions, the air clears. Rivers run cleaner where factories once drained them. Forests reclaim edges of highways. The carbon debt slows its climb. The sky regains a deeper blue. The atmosphere, always the most faithful recorder, writes this pause in quiet gratitude. The earth does not forgive, but it adjusts. And that adjustment becomes visible in every returning bird, every new leaf on a once blackened branch. In some regions, remnants of technology are worshipped like relics. Old data servers become temples of memory, their blinking lights replaced by candles. People recite fragments of code as if they were scripture, not for function, but for meaning. They are right in spirit; those lines once built a world. Others reject the past entirely, vowing never to rebuild the same machines. Between these poles lies the true path: remembrance without repetition, progress without arrogance. To an observer centuries later, the reset will look less like collapse and more like correction. Humanity's reach exceeded its understanding, and the planet answered by enforcing its limits. Yet within that boundary lies hope. The same species that ignited the fires also learned to live by their light. Balance returns, not as perfection, but as rhythm. There will be stories told of the time when the sky went dark, of the moment when cities became constellations of candles. They will sound like myth, but will be history. Children will ask what the world was like before, and the elders will pause before answering. They will remember both the marvel and the madness, the power and the price. And in that pause, perhaps, will lie wisdom. In the end, after the reset, the world does not end. It exhales. Civilization contracts, then begins again. quieter, but alive. The lesson lingers in the rhythm of windmills and the whisper of sails, in the measured hum of machines rebuilt with respect. The Earth has its breath back, and we are learning to breathe with it. The next step of the journey leaves survival behind and asks what it means, what it has always meant to build, knowing it will one day end, and to find meaning not in permanence, but in participation. The story turns toward reflection, into the final act, where the echo of these fires becomes philosophy. The world after the reset does not announce itself. It emerges slowly, like light through fog, rebuilding not from blueprints but from memory. Humanity has endured its trial, and the planet breathes again. Rivers flow cleaner, skies lose their haze, and nights grow truly dark. Yet the silence that follows recovery is not peace. It is contemplation. What does it mean to have come so far, only to circle back? What kind of wisdom can be built from ruins that still hum faintly with electricity? The remnants of the old world remain scattered. Towers half-lit by solar cells stand like markers of a forgotten ambition. Their empty offices overlook fields now reclaimed by grass and quiet. The relics of technology do not decay evenly. Some screens still glow when the sun hits them, reflecting faces that now recognize both loss and endurance. People move through these ruins like archaeologists of their own civilization, reading the patterns of pipes and cables as if decoding a language. They see that everything we built was designed for permanence, but permanence was never the planet's promise. In the first age, we measured success by accumulation. In the next, we may measure it by balance. The old system sought to grow without pause, mistaking speed for direction. The new mind that rises from the quiet understands that endurance is not stasis, but rhythm. Forests breathe in time with the soil, oceans move in cycles that take centuries, and the stars above remain steady only because of vast equilibrium. Perhaps civilization's next task is not to dominate those rhythms, but to join them. In plain terms, every collapse is a feedback loop closing. It is the universe adjusting a balance that has been tipped too long. To see that correction not as punishment but as dialogue requires humility, and humility may be the rarest form of intelligence. The survivors who rebuild know this instinctively. Their tools are fewer, their networks smaller, but their designs hum with restraint. Cities are born again, built where wind and water permit, not where pride demands. The return of light no longer feels like conquest. It feels like permission. They speak often of the old world, but not with bitterness. Instead, they treat it as a parent, flawed yet necessary, whose mistakes offered lessons that could not be learned any other way. The ruins become classrooms. Children learn that the glowing towers were not monuments to greed, but experiments in possibility. The lesson is not to avoid failure, but to fail better, to let the next attempt account for what the last one forgot. Civilization, seen this way, is not a line that climbs upward, but a spiral that deepens. Why does it matter? Because survival without reflection is repetition. The world can recover from disaster, but meaning must recover too. If the species rebuilds the same systems with the same blindness, the cycle will begin again. The philosophical echo of this age is a question whispered through every new machine: can we build with awareness of consequence? To create without worshiping creation, to use fire without assuming mastery, to love the world not as resource but as relationship. The philosopher of this new dawn might stand not in an academy but on a hill where windmills turn. She would look at their slow rotation and see not power, but patience. She would know that the measure of intelligence is not invention, but restraint. The old age worshipped speed and called it progress. The new one may find beauty in the pause, in the deliberate gaps between pulses. Music is not made by sound alone, it is made by the silence that shapes it. A generation after the reset, art begins to return, not as entertainment, but as remembrance. Sculptors carve from scrap steel, poets write in ash, Composers use the rhythm of turbines and tides as their metronome. They do not glorify collapse, but they do not hide it either. Their work asks what beauty means when built from remnants. The answer seems to lie in honesty. A cracked statue can still catch light. A broken circuit can still hum faintly when the wind passes through it. Imperfection becomes the new measure of grace. There are still arguments. Of course, some believe the age of machines should never return, that the world must remain simple to stay safe. Others argue that intelligence demands curiosity, that the act of creation is part of what makes us human. Between them lies the middle path, creation guided by awareness, technology grown inside, limits that honor balance. It is not an easy piece, but it is a functional one. Progress, at last, learns to whisper instead of shout. In everyday language, the meaning of the reset was never about ending. It was about remembering scale. The Earth does not need us, but it tolerates us when we listen. The stars do not notice our fires, but they mark our persistence. The cosmos is vast, and yet the smallest act of kindness, a seed planted, a tool repaired, a child taught aligns with its laws more perfectly than any machine ever could. The mystery of existence was never how we survived, but why we wanted to. At night, the world glows again, though dimmer. Small clusters of light mark human presence across the continents, not in grids but in constellations. Seen from orbit, they resemble stars reflected on water. The Earth has become what it once watched, a pattern of illumination fragile enough to flicker, strong enough to endure. The difference now is intent. We light the dark, not to prove power, but to share warmth. The boundary between sky and soil feels thinner than it once did. In this quieter world, philosophy steps out of books and into behavior. Ethics is no longer theoretical. It lives in architecture, agriculture, and conversation. To waste energy becomes an act of disrespect, not inefficiency. To harm a river feels like harming breath. The language of sustainability evolves into the language of belonging. We stop asking how much the planet can bear and begin asking how well we can listen. The echoes of science remain. We still watch the sun, measure its cycles, and trace the auroras when they appear. But now the awe is layered with gratitude. The sun is no longer enemy or god, but relative and elder whose storms once scolded us into awareness. The auroras are not warnings, but reminders. Soft veils of color that teach memory through beauty. Every flare we observe carries a whisper from the age when we thought control was the same as understanding. Why it matters is because meaning is all that remains when matter quiets down. The stars will continue to burn, the oceans to move, the winds to rise, whether or not humanity persists. What endures is not structure but story. The new civilization builds archives, not of conquest, but of context, how it felt to be here, between infinities, shaping and being shaped. In these records, there is humility. In humility, there is continuity. To put it another way, the universe is not a machine to master, but a mirror to read. Every storm, every spark, every collapse reflects the same lesson in different light that balance is not static, but dynamic. A dance of opposing forces seeking harmony. Our task is to join the dance without believing we lead it. If the Earth can remember us as a species that learned to listen, perhaps that will be enough. A poet of the New Age writes, "We are the brief silence between two waves, and the echo between two stars." The line travels far, repeated in classrooms and gatherings. It captures the feeling of a people who have learned to see themselves not as owners of a world, but as participants in its conversation. There is no triumph in that view, only belonging. The lights on Earth will one day dim again, and others may rise elsewhere. The universe will continue its patient work of creation and collapse. Perhaps somewhere, another intelligence will look up and wonder what came before it, just as we once did. Perhaps it will find fragments of our orbiting machines, silent witnesses drifting through darkness, still carrying our fingerprints. The final reflection is simple: existence is not a guarantee, but a gift. And the gift renews itself each time awareness meets awe. Our fires have burned, our networks have failed, and our songs have returned softer, closer to the pulse of the world. What remains is not despair, but curiosity. What else could the universe become, now that it has learned, through us, how to ask us? And so the story does not close. It continues in question form, suspended between breath and starlight. If the cosmos itself can learn, what might it be learning through us now?